Okay, welcome to problem 21 here. This is a problem concerning all the relationships that are within an ANOVA summary table. There's some value to this problem because you will find ANOVA summary tables in the literature. I must say, no two, there's a little bit of a snowflake factor going on here, in as much as no two seem to be alike. But once you start to understand what's on the interior there, generally you can go from one format to another and figure things out. So in this case, we've got a little problem scenario that I could read off to you there, but the only bit of information that's important to you is that there are 3 lakes in 3 groups. Okay, K is equal to 3 in this case. So let me get rid of that and get back to the light board. And let's just fill this out because this goes fairly quickly. First of all, if you come over to the sum of the squares, you see that you have a total and you have one value. So I can subtract one from the other. And if I did that, I think I get 14.19. I hope that's true. Let me take a second here. That is not true. That is 14. No, that is true. 14.19. All right. And then if you divide, then this mean squares can be found from these two values by dividing 9 into 14.19. I believe that's 1.58. All right. And then to fill out this value, remember these degrees of freedom. This is n minus k. This is k minus 1. We said at the outset that k is 3, so this is 2. And if I just divide 17.14 by 2, I get 8.52. Guess I could have done that in my head as well too. And then this f, the f ratio, the number that you're looking for here really is the ratio of 8.52 divided by 1.58, and that is 5.392. And that's the answer that you're looking for. All right, simple enough, yeah? Let's keep going. All right, on to problem 22, I believe. This problem says, let me read the scenario. It says when 25 randomly selected customers enter one of several waiting lines, their waiting times have a standard deviation of 5.35 minutes. When 16 randomly selected customers enter a single main waiting line, their waiting times have a standard deviation of 2.2 minutes. Use a 0.05 significance level to test the claim that there is more variation in the waiting times when several lines are used. Okay, so you've got two numbers, their standard deviations, 5.35, 2.2, clearly different. 5.35 clearly larger than 2.2, but again, what are we asking? We're asking if that difference is significant or not, and we have to do a significance test in order to do that. And this is a test of two variances, which makes use of the F distribution. So what it's asking us to do is to take a null hypothesis that says that sigma 1 is equal to sigma 2. Okay, or sometimes it's written sigma 1 minus sigma 2 is greater than 0. And in this case, we're going to let sigma 1 be equal to 5.35, and sigma 2 is going to be equal to 2.2. All right. The alternative hypothesis, again, if I just go back and read things, it says to test the claim that there is more variation in the waiting times when several lines are used. So that says sigma 1 is greater than sigma 2. And actually, I've got these in standard deviations. I should have put them in variances. All right? And so all that's really left to do with this problem is to find the F statistic and then make use of our calculator and the FCDF value to calculate a p-value, compare that to alpha. We said let's do this with 0.05. So let's calculate F. F is always the ratio of the variances, and generally you are instructed to set those up in such a manner that you have the larger of the two on top. I got to tell you, that's sort of historical, because when these values were found with tables, it was fairly easy to find the values out in the right tail. It was sort of a Byzantine method that you had to go through, not really that difficult, but somewhat not straightforward to find the information around the zero F, but the zero of the F distribution. But you just don't have to worry about that anymore. But I'm going to do it anyway. I'm going to set it up in this manner. So I'm realizing that I did this problem wrong when I first did it. So I'm going to go get the answer for the first time here. I'm going to calculate F right now, that's what I'm doing. And it comes out, this comes out 5.914. All right, so there's our F statistic. All we have to do now is go to FCDF, and in order to do that, we're going to go to second distribution, and we're going to find FCDF, and here I'll show you what we're going to do with it. So I am over to FCDF, I'm scrolling down, it's actually item number 10. Here's FCDF, and what it wants to know is what is the lower value, what is the upper value, what is the degrees of freedom for the numerator, and what's the degrees of freedom for the denominator. Okay, so let me fill these things in for you here now. I'd love to do that. So on the lower end is 5.914. And let me enter that real quick. 5.914. Yeah. Here is 1E99. I've already got that entered. The degrees of freedom in the numerator is the n number associated with the numerator, which was 25, minus 1, so that's 24. And the degrees of freedom for the denominator is the n number associated with the denominator, which was 16, minus 1, and that's 15. You get that over here. N1 was equal to 25, and N2 was equal to 16. All right, so I'm ready to push the button here and get out a p-value. And when I do that, when I need to do that, I get 0.000425. Okay, 4 times 10 to the minus 4 times 10 to the minus 4. All right, very small number. Very, very small number. So what that means, if I was to draw a picture, all right, here's the F distribution, all right, here's the p-value way over here. Wow, p equals 0.0004. And so what that says, since the p-value is significantly less than alpha, that says reject H0, right? So they go back to the problem statement. You look down to answer D, it says the test statistic is 5.91, the p-value is 10 to the minus 4, reject H0. There's sufficient evidence to support the claim that there is more variation in the waiting times when several lines are used. Okay? Takes a little time, but straightforward exercise, I think. All right, very good.